The previous section, section 9.2, was about testing the differences of two proportions. And remember, the big question was, which also applies to this section and the subsequent section, when there is a difference in the samples, is the sample difference significant enough to say there is a difference in the two populations? And remember, in the end, it's always about the populations. So this section tests the difference of two means with independent samples. And so we are looking at examples of independent ones. And so here's the conditions for samples to be independent. So here's the formal definition. Two samples are independent when members of one sample do not dictate which individuals are to be in the second sample. And we will look at some examples in just a moment. Meanwhile, let's define what it means to have dependent samples. So here's the definition of dependent samples. Samples are dependent when individuals in one sample are used to determine the individuals in the second sample. That sounds all very formal, and obviously there has to be a formal definition, but when you look at examples, it's pretty intuitive. I added something to make it more understandable. We can also say that each data value of one sample is matched or paired with the data value of the other sample. So, for example, compare memory test results of treatment group taking oral supplements versus a control group taking placebo. That would be an example of an independent sample. Independent. When we compare the memory test results of treatment group before and after taking herbal supplements, there would be a dependent sample because it's the same group. Dependent. And then compare daily average internet time for male versus female students. That, of course, would also be independent because the groups don't depend on each other in the terms of internet use. Independent. And when you compare the mean weight loss of 40 clients from Weight Watchers versus 32 clients from Jenny Craig, these are independent groups. Independent. And I think your intuition is pretty good about these things. It's not very formalistic. Or compare on task time for students in blue room versus the same class in the red room. Well, that of course would be the same group, so that would be dependent. Dependent. And compare the average score on the standardized test for a group of 50 students before and after study program. Again, that's the same group, so it would be dependent. And the last one asks, compare the average price of a one-night stay at a Holiday Inn Express hotel to a Red Roof Inn hotel in the same town. And you randomly select 8 towns. That would be a case for a dependent sample because the prices probably influence each other. Dependent. So first we're going to look at a sample t-test where sigmas are known. And so here are the conditions. A hypothesis test for the difference of two means is a two-sample t-test if the two samples are randomly selected, if the two samples are independent, And if the two populations have a normal distribution or both our sample sizes are large, like n1 equal to 30 and n2 equal to 30. So the test statistic is x1 bar, the sample mean for the first sample, minus the sample mean for the second sample, divided by the standard deviation for the test. Standard deviation for the test. And the standard deviation for the test is unpooled. So the population variances are not necessarily equal. And so in that case, the standard deviation is equal to the square root of s sub 1 squared, divided by n sub 1 plus s sub 2 squared divided by n sub 2. And of course, degrees of freedom is, in this case, the smallest n, the smallest of the two n's, n1 or n2, smallest of n, minus 1. Then another method which allows us to pool the standard deviation requires, though, that the population variances are equal, which is hardly ever the case when you talk about independent samples. So the test for whether variances can be considered equal can be applied only to very narrow circumstances. So we, won't get a whole lot into that. And here's a heads up about the pooling population variances. The test for whether variances can be considered equal can be applied only in very narrow circumstances. In other words, it is not robust. By using unpooled is a more conservative approach that can be used whether the variances are equal or not. And by the way, the variance is the square of the standard deviation. Just a little reminder. Regarding the degrees of freedom, when we use the smallest of the n1 or n2, it gives us a conservative approximation for degrees of freedom. There's a much more complicated formula for degrees of freedom, which you probably don't want to use if you do things manually, but it is built into, into many of the calculators. So that is why you may see, if you use technology, degrees of freedom, in case that appears in the results section, it may be different than if you use the n minus 1, n sub 1 minus 1, or n sub 2 minus 1, the smaller of which you would use. Let's look at an example. This is about herbal supplements for memory. To test the effect of an herbal treatment on improvement of memory, you randomly select a sample of 95 to receive the treatment and a sample of 105 to receive a placebo. Both groups receive a test after 1 month. So obviously these two groups are independent, so establish that part. Now the mean score for the experimental group is 77 with a standard deviation of 15, and for the control group the mean is 73 with a standard deviation of 12. Test the claim that the herbal treatment improves memory at alpha equal to 0.01 or 1%. So here's our data summarized. Here's a treatment group and the placebo group and the sample mean for each group, 77 and 73 respectively. Also the sample standard deviation of 15 and 12, and the number of samples, n being 95 and 105. So here we have our data neatly organized, and now it's time to write our hypotheses. And so our null hypothesis is mu sub 1 equals mu sub 2. And for the alternative hypothesis, the claim is that mu sub 1 is greater than mu sub 2. So that is the claim that we want to investigate. So let's draw a graph and include our critical values. So the step now is to graph our t-curve, our t-distribution. And so it's a right-tailed one indicated by the alternative hypothesis, with the rejection region beginning here at the critical value. And so degrees of freedom would be the smallest of the n values, 105, 95. Obviously 95 is the smallest. And so 95 minus 1 is 94. That is our degrees of freedom. And for an alpha level of 0.01, whether we use the table or use technology, the critical value is 2.367. 2.367. So that's the beginning of the rejection region here, which is all of this tail here. Using technology, we find that our test statistic is t equal to 2.068, and the associated p-value is equal to 0.02 for the p-value, and so it's number 4. And so we look at the test statistic, and that tells us that we are not into the rejection region. So in other words, this tells us that we failed to reject the null hypothesis. Similarly, our p-value is not less than alpha. In other words, 0.02 is not less than 0.01. So that's a no. So in other words, on both counts, the test statistic and the p-value, we fail to reject the null hypothesis. That's 5. Fail to reject the null hypothesis. So that is our decision here. Yeah. And now we're ready to state our conclusion. At the 1% level of significance, there's not sufficient evidence to support the claim that the Erbe treatment improves memory. Another way of phrasing it is to say, at the 1% level of significance, this data does not provide significant evidence that the mean memory score for the experimental group is greater than the mean score for the control group. The next example is about comparing teaching methods, and so it tests the claim that teaching method A results in lower test scores than method B, based on the following summary statistics with alpha equals 0.05 or 5%. I find it useful to arrange the data, but if it's given to you this way, or like in the previous example, you have to write it down, but to also include what the mean test score means in terms of the mean mu sub 1 and mu sub 2, which one belongs to which one. So now we are ready to write our hypothesis. 1 is the hypothesis. So our null hypothesis is that mu sub 1 equals mu sub 2, and the alternative hypothesis is that mu sub 1 is less than mu sub 2, due to the problem statement. Yeah. So that tells us we have a left tail distribution. So let's draw the t distribution and the rejection region and find the t critical value. So it's alpha being 0.05 and degrees of freedom is 32 minus 1 because 32 is the smaller of the two values of n1 and n2. And that gives us a critical value for t of minus 1.696. So this is minus 1.696. Using technology, our test statistic is t equals minus 5.287, and our p-value is p-value is 0.123455. That's our p-value. That's a 0. So let's look at the results here. So the question is, does this test statistic tell us we are in the rejection region or not? Clearly, minus 5.2 is way into the rejection region. In other words, that tells us we reject the null hypothesis. And since the p-value is less than alpha, alpha being 0.05, that also says we should reject the null hypothesis. So reject, that's our decision, reject the null hypothesis. In fact, some people might even say strongly reject the null hypothesis because the p-value is so much smaller than alpha, and also the test statistic is way into the left tail here. So in other words, the probability of finding anything to the left of that is extremely small. So we certainly reject the null hypothesis. Now we can state our conclusion, which is, with 5% level of significance, this data does provide significant evidence that teaching method A results in lower mean test scores than the mean test scores from method B. So here it is written for you, with 5% level of significance, this data does provide significant evidence that teaching method A results in lower mean test scores than the mean test scores from method B. To answer the next question, find the corresponding percent confidence interval for the difference in mean test scores, mu sub 1 minus mu sub 2, under the two teaching methods, method A minus method B. We need to remember that we had a left tail distribution with 0.05 in the left tail. So let me just draw it out real quick here. And remember, for the confidence interval, we need to balance this 0.05 on the left with another 0.05 on the right, which means we have 90% in the middle. So we're looking for a 90% confidence interval. And when we do that using technology, we get the following results. Using technology, our confidence interval for mu sub 1 minus mu sub 2 is from minus 5.532 to minus 2.867. So both endpoints are negative. If we round it, of course, it would be minus 5.5 less than mu sub 1 minus mu sub 2. In other words, the difference between the two scores, and minus 2.9. And this would then be saying that with 90% confidence, this data predicts that teaching method A results in mean test scores between 2.9% and 2.9 points and 5.5 points lower than teaching method B on average. So let me write that down for you. So again, looking at the confidence interval, we can say with 90% confidence, this data predicts that teaching method A results in mean test scores between 2.9 and 5.5 points lower than teaching method B on average. Here's one more example for section 9.3. Crash tests at 5 miles per hour were performed on 5 small pickups and 8 SUVs. For the small pickups, the mean bumper repair cost was $1,520 and the standard deviation was $403. For the SUVs, the mean bumper repair cost was $937 and the standard deviation was $382. At alpha equals 0.05, tests claim that the bumper repair cost is greater for small pickups than for SUVs. I added to the given data mu sub 1 and mu sub 2 to indicate that that's the mean bumper repair cost for the pickup, mu sub 1, and for the SUVs would be mu sub 2. So now we're ready to write our hypothesis. And so our null hypothesis is mu sub 1 equals mu sub 2. And the alternative hypothesis is mu sub 1 is greater than mu sub 2. So mu sub 1 is greater than mu sub 2. So we have a right-tailed distribution. So let's graph that one. And sketch on the rejection region. So this is what it looks like. Our degrees of freedom is 5, the smaller of the two values for n. Minus 1 equals 4. And for an alpha 0.05, we find that our critical value for t is 2.132. So that's what t is. T is equal to 2.132. So this is our rejection region here. When we compute our test statistic, t, it is, using technology, it is 2.589, and our corresponding p-value is equal to 0.0157. Point 0.0157. With the test statistic of 2.589, we are clearly in the rejection region, so that would suggest we reject the null hypothesis. Also, the p-value is less than alpha, 0.05, which also suggests to reject the null hypothesis. So then our decision is reject the null hypothesis. So now we're ready to state our conclusion. With 5% level of significance, this data does provide significant evidence that the mean bumper repair cost for small pickups is greater than the mean bumper repair cost for SUVs. The next question is find the corresponding confidence interval for the difference in mean bumper repair costs. And again, what we have to keep in mind, like in the previous example, we have a right-tailed distribution here. And for the confidence interval, we need to balance this 5% on the right with 5% on the left, which means we have 90% in the middle. So in other words, we find the corresponding 90% confidence interval. Using technology, we find that our confidence interval is from 165.93 to 1001.1. In other words, the difference in mean bumper repair cost is between $166 and $1,000 on average. So here it is for you in writing with 90% confidence. This data predicts that repairing the bumper on a small pickup will cost between $166 and $1,000 more than repairing the bumper on an SUV on average. And this concludes section 9.3.